Hello, everybody. So my name is Sutapa. I'm a faculty in the physics discipline at IIT Gandhinagar. And so I work on statistical mechanics and theoretical soft condensed matter. And so mainly for that, I use different computational tools like molecular dynamics, Monte Carlo simulations, etc. So that's the main topic of the broader perspective of the work that I carry out. And like you know, so in this theoretical physics school, I'm going to talk about the dynamics of confined fluids, yeah, which are close to phase transitions. Now, so what I mean by these confined fluids, which you see in the title of the talk, is basically fluids which are in contact with surfaces. Huh? And as we go on, we'll see what we really mean by these, what are the properties of these fluids which have, the surface properties. And we'll also see in detail what do I mean by phase transitions, yeah? And this is actually a pretty active field of research at the moment, if you look at the scientific community all over the world. And it's something which is mainly relevant for nanofluidics, for device manufacturing and soft condensed matter, and has had very interesting applications in biological systems. Okay, so the plan of the talk is the following. So just 1 minute, please. So is the slides okay, Sudipta, or it's not in the full screen mode?
I think it's okay. Yeah, maybe you can look at the edit, make it. I think it's full screen, right? It is clearly visible. Yeah.
Okay. Fine. All right. So the plan of the 5 lectures is the following. So I'll start with the basics of phase transitions and confined fluids. Yeah, and these are some of the things which probably some of you are already familiar with in your, in your textbook stuff, basically. And since I assume that most of you are MSc students, so I'll start with the very simple things, the elementary stuff, which we'll cover mainly today. And starting with those textbook stuffs, then I'll lead you to the rather advanced part of the topic, okay, which will be covered in the first, starting from tomorrow mainly. And finally, I'll lead you to the interesting new research activities which are going on in different scientific groups. So that's the basic idea for the 5 days. And I hope that some of you will find it interesting and, to try to understand how the things which you learn in the textbook stuffs are actually connected with the recent scientific works which are being done by scientists all over the world. And that will probably make you interested in pursuing science and academia as your future career, hopefully. So, yeah, so this is mainly the plan of the 5 days lecture series. So today I'll give you an introduction to the confined fluids, which are what are the different properties of these confined fluids. I'll give you some examples of some of the systems, and I'll explain what do we mean by phase transitions. Then from tomorrow onwards, we'll get into the properties, different kind of static and dynamic properties of such systems. We'll focus both the equilibrium systems as well as non-equilibrium systems. And on the last day, I'll give you a brief overview of very recent scientific works, from which are done in the very prominent groups all over the world. Okay, so today's talk is mostly going to be a rather shorter talk because it's going to be elementary. From tomorrow onwards, it's going to be rather more involved. And before I begin, so let's just set a couple of rules for the talks. So please mute your microphones while the lecture is going on. Yeah, and if you have any questions during the talk, then please put those on the on the chat box. So I'll have a look at the questions and I'll get back to you. At the end, there will be a question answer session where also you can write the questions on the chat box and I'll get back to you. Okay. If you have any questions later, please feel free to send email to my email address, which is roy@iitgn.ac.in. Okay. All right. So with that, let's begin with the basic introduction of confined fluids and phase transitions. All right. So let me first try to give you a few examples of these confined fluids. Yeah, what do we really mean by such systems? Well, it basically means fluids which are in contact with surfaces. Yeah, and by surfaces, I actually refer to the solid surfaces. Now, the fluids can be of different types. So, what are typically of interest to people are it can be either binary fluid. What we mean by binary is that it's a fluid which has two types of particles. Okay, say for example, oil and water types of. So you can you can you can refer to them as say the A and B type of particles, or they can be simple liquids. Okay. Now, if you look at this picture here, that's what is being shown schematically. For example, you have two type of particles here. The pink one, let's say it corresponds to the A type, and the blue one, say it corresponds to the B type. Okay. And these two different types of the fluid, which is consisting of these two different type of particles, you put that into confinement in between two slabs. Okay. And these slabs or the surfaces prefer, say, the A type of particles, which are basically the pink type of particles. Okay. And then if you look at the properties or the configuration of the system, what you find is basically that all the pink particles, or let's say the A type of particles, they go towards the surfaces, they get absorbed there, and you get nice layers of the A type of particles on top of the walls. Okay. Now, the important and the interesting questions are, of course, what are the properties of this kind of system, when the non-equilibrium dynamics of this, the formation of this kind of layering is going on, or in other words, which are the properties of such systems in equilibrium as well. And you can have this example that I show you, it's mainly for binary fluid. You can have similar phenomenon for simple liquids, say, for example, just one type of particles as well. Okay. So the interesting key feature here is mainly the adsorption of this fluid on this solid substrate. Yeah. And the question is, what are the properties of these kinds of adsorption phenomena? So that is something which we will look at in this lecture series. And one thing to note here is that when you have this kind of surfaces, okay, you get a breaking of the translational symmetry of the system. So if you have a bulk system, okay, you know that there is some kind of translational symmetry. But the moment you put surfaces, this translational symmetry gets broken. And we will see what are the consequences of such symmetry breaking. So this is one example which we will pick up tomorrow. Another example of confined fluids, which is actually very interesting and a very hot topic at the moment, is something called colloidal particles, which are suspended in solvents. Okay. And what do I mean by colloids? Well, the colloids are basically microscopically dispersed particles of one substance, which are suspended in another substance. Okay. So these are some particles which are basically suspended in a solvent. And typically their size ranges in between, say, 1 to 1000 nanometer. Yeah. Now, to give you an example here, so for example, say you take one such colloidal particle, and it's called a Janus colloidal particle, in the sense that if you look at this particle and you look at its right hemisphere and the left hemisphere, the properties on the both sides are going to be different. Okay. So you take a particle like that, a Janus particle, and you suspended it in a solvent. Okay. And then you shine laser on top of the particle. So what one observes in such situations is that there is a formation of an asymmetric structure around this colloidal particle, like you see here. And then this particle starts to undergo active motion. What I mean by that is that when you take the particle, put it in the solvent, turn on the laser, you suddenly see that the particle starts moving, in a certain direction. And you have layers of the solvent which starts forming around the particle, like you see in this picture here. So in the next picture, it's the what I show you is basically the non-equilibrium phenomenon which is going on around this colloidal particle. You see the formation of layers, which are marked by different colors here, the red and the blue colors mainly. which corresponds to different species of the solvent. So you have this kind of layering effects, layers form, those layers get thicker and thicker, then the layers break, and finally you get some kind of bubble formation and layering, etc. So it's a pretty complex and very interesting non-equilibrium phenomena which go on around such hot Janus colloidal particles. Okay, and the confinement effect in such system basically comes from the fact that if you look at these particles, they have a certain preference for surface affinity to one of the components of the solvent, which means that these particles, the surfaces of this particle, they give rise to some kind of confinement effect. If you look at the dynamics of the solvent surrounding it. So this is one example, which is a pretty hot topic at the moment in the community, and we will get back to it later during the talks. Another interesting phenomenon for confined fluids is something called liquid bridge formation. So what do I mean by that? One good example is once again with colloidal particles. So you take a colloidal particle and you put it in confinement. What do we mean by that? You take the colloidal particle, which is marked by the gray color here, and put it in between two glass slabs. All right. So you have two glass slabs. You put the particle in between, and you have the solvent surrounding the colloidal particle. And under such situations, under certain conditions, you start observing that layers form mainly around the particle, like you see here. So the different colors here, the green and the yellow color, they correspond to different species of the solvent once again. And you see that basically it's a non-equilibrium phenomenon which goes on around the confined colloid, where you see layers of certain type of particles, namely say the green particles, start forming on top of the glass slabs as well as the colloidal particles. As time progresses, these layers get thicker and thicker. You have more this kind of structures which form around the particle. And finally, as you see here, if you look at the two glass slabs, you see that the layers which are forming on the top slab and the bottom slab, they get connected and the colloidal particle gets trapped in between. And this kind of formation of the layer, which basically combine the entire particle, it's called liquid bridge formation. Okay, and we will see what we mean by this liquid bridge formation and how is it related to some kind of weighting phenomenon, etc. All right, so this is an example of confined fluids which people work on. Another example is something which is known as surface-directed spinodal decomposition. So what do we mean by that? It's something which is related to the term called phase separation. Okay. So namely, say for example, you have a liquid and this liquid is in contact with a surface which is marked by the yellow slab here. And this yellow slab, or say the surface, it has a preferential attraction to the one of the two components of the fluid, which is here. Let's say it attracts the black particles more towards it. Okay. So you take the fluid, put it into confinement, and then you basically quench this kind of system from a high temperature to a low temperature below the demixing critical temperature. And don't worry about this terminology now. If you don't understand, we'll get back to it later. So under certain conditions, if you do a temperature quench, if you change the temperature of the system suddenly following certain rules, what you see is that structures of this kind, or rather the domains, start forming in the system. Okay. So first of all, you get the formation of a layer of the black particles on top of the surface. And away from the surface, you have formation of the domains of the black particles and the white going on in the system. And this phenomenon is known as surface-directed spinodal decomposition. It's spinodal decomposition in the sense that this kind of domain formation, which you see here, it's called spinodal decomposition. And in this particular case, for a confined fluid, the properties of these confining surfaces have a huge impact on the properties of this phenomena. So that's why the term surface-directed comes into the picture. Now, what are the properties of these domains which are forming? Are they really going to be droplet-like you see in the second picture here? You see just some kind of disconnected droplets which have formed in the fluid, right? So it can either be a droplet or it can be continuous percolating structure like you see in the first picture here. That depends on the properties of the fluid and certain, concentrations, etc. of the fluid. So those are some subtle, minute details, but this, depending on that, you can have this kind of phase separation or this kind of structure formation going on in the system. And it's known as surface-directed spinodal decomposition. So these are some of the examples of the confined fluids, which people typically in this field work on. And during the lectures later, I'll pick up some of those examples, which I showed you just now, and we will revisit them in greater detail. Okay, we'll try to understand why this kind of phenomena happen and what are the properties of those things. All right, so next what we'll do today is basically, if you remember, I told you that all these confined fluids which we are going to talk about, they are going to be close to some kind of phase transition, okay? So the fluids are mainly going to be close to phase transition temperature. So the first which we will do now is to recap what we mean by phase transitions and phases. And this is something I assume that most of you have already come across in your MSc classes in the textbook. Nevertheless, I'm going to give you a brief recap of those things. Might be a bit newer as well to some of you. So let's get into the first topic, which is mainly phases and phase transitions. Okay. So what do we mean by phases? Well, like you know, matter exists in different phases, right? It can be solid, liquid, or vapor or gaseous phases, depending on different system parameters. And whenever you have a transition from one of those phases to the other, it's called a phase transition, right? Now, a typical example, like you know, in your daily life, that you take out the ice cubes from the fridge and you put it on the table at room temperature, after a few minutes, it just melts, right? Which means that from the solid phase, it goes to the liquid phase. So that's one kind of phase transition. You take the same liquid and you put it for boiling on the stove, and you know that after a few minutes, it just starts to boil. So that's another kind of phase transition, which is basically liquid to the vapor phase. Yeah. And in this picture here, in the cartoon-like picture, what I show you is mainly the different phases of the normal water system, where you see mainly all the three phases: the solid phase, which is the ice, the liquid phase, which is the water, and of course the vapor phase, which you don't see here. And whenever you have a transition from one of these phases to the other, that's something which is known as phase transition. Now, this is an example of a phase transition for a normal liquid system, say water-like system. You can have similar kind of phase transition for magnetic systems as well, okay? Like, for example, I hope you have already come across the term paramagnetic and ferromagnetic systems. You know that there exists a certain temperature, which is called the Curie temperature, above which, if you look at a magnetic system, certain kinds of magnetic systems, it's mainly the order parameter is 0, or the spins are just randomly oriented. And if you change the temperature, it mainly goes into an ordered phase where all the spins just start aligning up into a certain direction. So that's another example of another kind of phase transition, which we will come to. But for the time being now, first, let's just focus on the simple liquids, okay? So how does the phase diagram of this kind of simple liquid look like? Okay, that's what we show here in the pressure temperature plane. And these curved lines, which you see here, so those are mainly the coexistence curves, okay? What do we mean by that? The two different phases, namely say the solid, the liquid, solid or gas, or the liquid or gas, they can coexist with each other along these lines in equilibrium, okay? Now, the different phases, solid, liquid, and the vapor phases are already marked here, like you know. What's interesting here is that this dashed curve, which you see here, which is mainly known as the melting curve, yeah? So that's the coexistence between the solid and the liquid phases. This melting curve actually continues forever, whereas if you look at the liquid and the vapor coexistence curve, this curve actually actually terminates at a certain point, which is known as the critical point. Okay, and at this point, the critical point and beyond it, if you look at the liquid and the gas phases, there's no density difference between the two. Okay, so one can always go from the liquid phase to the gas phase without encountering any kind of jump in the density. Okay, and in this particular case, the order parameter is actually the density difference between the two phases. Okay, so what is an order parameter? An order parameter is mainly a parameter that one defines to distinguish or to quantify the kind of transition which is going on at this point, namely the critical point. Okay, so above the critical point, this order parameter is mainly 0, like I explained to you. If you are at the critical point or beyond it, there's no density difference between the liquid and the gas phases, so the order parameter is 0. And below it, below the critical temperature, the order parameter is finite. Okay. So if you look at this kind of transition here at the critical point, like you see that the change from the liquid phase to the gas phase does not encounter any kind of discontinuity in the order parameter. And that's why this kind of transition is known as a continuous phase transition. Okay. And this type of transition is also known as a second order phase transition. I will not get into the detail of that. If you want to know, then I will just urge you to pick up any textbook on statistical mechanics and just have a look at the the phase diagram and the phase transition part. And please do that actually as a homework, and then try to see if you can understand why this continuous phase transition is known as a second order phase transition. Okay, so please take that as the homework for today evening. Just to give you a hint, why is it the second order phase transition? This order parameter that you are looking at, that's a derivative of the free energy. So you can always relate it to the free energy, and the question is which order derivative is actually becoming discontinuous. Okay, so that will lead to the order of this transition which you are looking at, whether it's the first order phase transition or second order phase transition, etc. So I'll leave it to you as a homework for today evening. Please try to figure it out why this continuous phase transition is also known as a second order phase transition. Okay. Now, two more questions, two more homeworks for you. Please try to find out what are the properties of this triple point. So the triple point is mainly the point where these three coexistence curves, namely the sublimation curve, the solid gas one, the melting curve, the solid liquid, and the liquid vapor curve, they all meet at one particular point. Okay, so that's what is known as the triple point. So please try to find out what are the properties of this triple point. Okay, and the final question, the task which I leave for you is to look at the curvature of the solid liquid coexistence curve. Please try to find out for which kind of systems it's going to be, either if the curvature is going to be positive or it's going to be negative. Okay. For example, if I give you two systems, one is a normal water, or I give you a magnetic system, the curvature is going to be same for the two different type of systems. Okay. So these are three questions which you must look at today evening, and we're going to look at the answers of these three questions tomorrow when the lecture starts. So nevertheless, so these are mainly the properties of the a normal chemical system or a water-like system. It's the phase diagram in the pressure temperature plane. Okay. Now, if you remember, I was talking about the magnetic system before, right? And I hope you have already come across these terms in your statistical mechanics course in MSc physics classes. So you know that there is something called paramagnetic and ferromagnetic systems. So if you look at these magnetic systems, you can actually map it onto in terms of certain lattices, right? And that's what is being shown here. So for a ferromagnetic system, namely, these lattices are actually all they are aligned into one particular direction. Whereas if you have the paramagnetic, it's mainly disordered, right? So it can align in any direction. What it means is that if I look at the order parameter of such a system, and the order parameter here is actually going to be the average magnetization. So if I look at it for a paramagnetic system, it's going to be 0 because they are just randomly oriented. Whereas if I look at a ferromagnetic, it's actually going to be something of a finite value because they are all aligned into one particular direction. Now you can imagine a situation where suppose you have a system where things are perfectly, things are just, they are randomly oriented initially. So you have a state like that, and then you suddenly change the temperature of the system. And to specify, if you actually quench the system below a certain temperature, which is known as the Curie temperature, then these lattices basically get aligned, and you have the system where the magnetization is of finite value. So that is another kind of phase transition, where starting from this randomly oriented phase, you are going to a ordered kind of phase. Okay, so that's a phase transition which one observes in case of a magnetic system. All right. So let's come back to the fluid-like systems once again, because in our talk, we will, in the lecture series, we will mainly focus on fluids only. Now, to mention here basically, so what do we mean by the difference between the solids and the fluids? Well, when I mean fluids, what I mean is that it has some kind of hydrodynamic effects. Okay, so for the solids, for example, you know that the atoms cannot really move, but in case of a fluid, there is a mobility, which means that, and you have hydrodynamics conservation, which means that you have mass, momentum, and energy conservation in the system. So we will come back to those things later as we go on as well. For the time being, just please keep in mind that in the lecture series, we're going to focus on only fluids, okay? So if you look at the phase diagram of such a fluid system in a different plane, so earlier the phase diagram was in the pressure temperature plane. Now let's focus on the temperature concentration plane. Okay, how does it look like? And what do I mean by the concentration? Well, like I told you, it's a binary fluid, right? Which means that it has two types of particles. It has A type of particle as well as B type of particles. So the concentration is basically the relative number of A type of particles as compared to the total number A and B. Okay. So let's have a look at this picture here. This pink curved line here, that corresponds to the coexistence curve, along which the A and B phases can coexist with each other. And this TC here, that corresponds to the critical temperature, which I explained to you earlier in the pressure temperature diagram. Okay, so if you look at if you remember the phase diagram which I showed you here, this point here, which is marked by the this red dashed, the part here, this point corresponds to the critical temperature, which I explained to you. And the phase diagram that we look at is actually going to be close to this particular critical point, but in a different plane, which is the temperature concentration plane. So this TC here corresponds to the same critical temperature that you saw in the other phase diagram. Okay. Now, first of all, when the system is at a temperature which is higher than this critical temperature, you have the two phases A and B, which are perfectly mixed with each other. So it's a perfectly homogeneous system, which you see here. Okay. Now take the system, which is initially homogeneous, and then you suddenly quench the temperature from a high temperature to a temperature which is below the critical temperature. Or in other words, you are quenching the system inside this pink line, the pink curve line, which is also known as the binodal curve. Okay. Once you quench it below this critical temperature, the system then enters into the two-phase coexistence region, which means that you have this A and B type of phases, which are mainly say marked by the red and the yellow type of particles here. They can then coexist with each other. And you clearly see the domains of A and B type of particles separately. It's no longer homogeneously mixed, and you have the two different domains very distinct from each other, right? And the right part of this binodal curve here, that corresponds to the A type of phase, okay? And the left part corresponds to the B phase. And these A and B phases can now coexist with each other. So these are going to be some of the properties of the phase diagram of a normal binary liquid mixture. And this is going to be important for the rest of the talk, because we are going to consider a binary liquid which is going to be in close proximity to the critical point. All right. So at this point, I would like to stop for 5 minutes and take the questions if you have any. So let me just try to see if there are any questions. If you have any questions, you can just put it on the chat box and I can address the questions before we proceed further. Mhm. So there is a question by Naman Agarwal that in the binodal curve, can you see the coexistence curve of the two phases? Yes, of course. That's what is the binodal curve. Yeah. So this binodal curve, which you see here, it actually corresponds to the coexistence between the A and B phases. Okay. Yes, it's equilibrium. Okay. Then the next question is that can you please explain the surface-directed spinodal decomposition once again? Okay. So basically, now that you have already, I showed you the phase diagram of this binary liquid mixture, probably I can, it will be much easier for you to understand what do we mean by the surface-directed spinodal decomposition. So let's say, for example, we take this binary liquid mixture, okay? And we know the phase diagram of this system now. There is a certain temperature called T, above which the fluid is in the mixed phase, and below it, it's in the two-phase coexistence region. Okay, so if my fluid is at a temperature which is below the critical temperature, I'm going to have domains of A and B particles which are going to coexist with each other, right? Now, what happens in case of a surface-directed spinodal decomposition? You take this same binary liquid mixture and you say, for example, put it in confinement or in contact with one surface. All right. Now, initially, let's say I keep this fluid at a temperature which is higher than the critical temperature, which means that the system is basically homogeneously mixed, right? Now, suddenly I change the temperature of the system from this high temperature to a temperature which is below the critical temperature. Okay. Then what happens? Now there is the system will actually try to form domains of A and B particles because it now corresponds to the two-phase coexistence part. Okay. Now, if you look at the if you look at the system here, so basically this fluid now I have kept in contact with a surface. And let's say this surface actually prefers the A type of particles, which are mainly say the black particles. Okay. Because of which, because the surfaces now prefer the A particles more, you will have a layer of A particles forming on top of the surface. All right. Now, what happens away from the surface? So as you go further away from the surface, this affinity of the surface to attract the A particles, that affinity also decreases, right? Why? Because the distance of the particles from the surface is increasing, right? So this affinity of the surface to attract the A particles more towards it is getting lower and lower as you are going further away from the surface. So in the bulk, or not bulk, say for example, further away from the surface, what happens is that you have domains of these A and B type of particles, namely the black and the white, forming. And why are the domains forming? Because now you have the temperature of the system, which is inside the coexistence, the binodal region. Okay. And that at that temperature, the system is supposed to show you the domains of A and B type of particles, which are going to coexist with each other, because that's the property of the system at that temperature. So that's why you have this kind of domains forming, like you see in both the pictures here. You can either have percolating continuous kind of domains, or you can have disconnected droplets. Now the question is, under which situations are you going to have percolating structures like you see here, or you're going to have droplet-like structures? So to understand that, let's go back to the phase diagram once again. If your system is exactly at the critical concentration, by which I mark this point here, okay? So if it's the concentration, which is actually corresponding to this critical temperature, the critical concentration here, if your fluid is exactly at the critical concentration, then you are going to have percolating kind of structure, which means the first kind of situation, okay, where you have the domains which are very much connected to each other. On the other hand, if you have a system where the fluid concentration is away from the critical value, let's say your fluid is somewhere here, okay, so that's called the off critical concentration, okay, the terminology is off critical. So if you have an off critical concentration, in such a situation, you are going to have droplet-like structures, okay. All right. So let's say I'm just trying to pick up the other questions which are already here. Okay, so there is a question by Rajnil Barua. Are the domain formations mentioned in the surface-directed spinodal decomposition something similar to domain wall formation? Yes, of course. What do you mean by phase separation? So the term phase separation is directly related to the domain formation. When you have phase separation going on, you have basically domains of A and P particles or the different phases which are forming, right? So initially you will have domains which are pretty small, then the domains will get bigger and bigger, and those domains might get again connected with each other, until and unless you have a very large domain, single domain, which is existing in the system. So yes, you are right. The spinodal decomposition, which I'm talking about, it is connected to the domain formation. And when you have two domains in the intermediate region, you have a domain wall, right? So that's what is meant by the domain wall. Okay, so there is a question by Soham in the same direction. So how is the domain formation? Is the domain formation responsible for phase separation? Yes, of course. So you have the domains forming, and those domains are coming close to each other, and you have a bigger domain which is forming. That's what is known as phase separation. Yeah. So basically, the phase separation process, which is a non-equilibrium phenomenon, by the way, the phase separation process goes on by the formation of domains. All right. Okay. So that's all the questions which we have now. So let's then continue with the things which we were talking about before. Okay, there is a question. Please refer to the slide of spinodal decomposition for phase separation and domain formation. All right, very good. So that's actually the slide which I was planning to come back to later, trying to explain to you why you have this kind of spinodal decomposition forming. But since we have the question, maybe I'll take up that question first, and I will just explain you why the spinodal decomposition happens. Yeah. Okay. So the first schematic picture here, I show you once again the phase diagram of this the binary liquid mixture. Once again, Tc corresponds to the critical temperature. Above the critical temperature, you have the system which is homogeneously mixed, and below the critical temperature, it's in the demixed state. Yeah. And the x-axis here is the concentration of the A particles, which is defined here, which is mainly the ratio of the number of A particles to the total number of particles. And the y-axis is the temperature, like before. So this is the same phase diagram that I showed you before. Now, the question is, if you take the system, which is at a very high temperature, and then you quench it, why does the spinodal decomposition, or why does the phase separation happen at all? Yeah, and that's the questions which many of you, 2-3 questions have already been posted in the chat box. So let's try to find out the answer to that question. Now, in order to understand that, let's have a look at the free energy. So something which is known as the Landau free energy, which I'm sure you must have come across in your statistical mechanics course. If not, please don't worry about it. So the Landau free energy is actually a free energy which is given by this equation here. Psi is the order parameter, which I explained to you before. So the order parameter is a parameter which actually used to define some kind of phase transition. Above the critical temperature, it's mainly 0, and so in the disordered phase, it's 0, and in the ordered phase, its value is non-zero. So in this equation here, T is the system temperature, Tc is the critical temperature of the system. Now, if you look at the functional form of this Landau free energy, that's what is plotted here. Depending on the temperature, whether the system temperature T is higher than the critical temperature or lower, the functional form changes, right? Now, if T is higher than the critical temperature, that means that the first term here, which is associated to the square term, that's positive. So you have both square and fourth order terms. And the functional form of the free energy is given by the green line here. It looks like this. And you have only one minimum, right? If the temperature is exactly at the critical temperature, by the first term, it basically drops out, it becomes 0. The functional form is given by the blue line here. And if the system is below the critical temperature, all right, which means when the temperature T is actually lower than the critical temperature, which means that the first term is actually the coefficient here will become negative, which means that it's going to be minus psi square plus psi to the power 4. And in such situation, the functional form looks like this. So you have two minimum and there is one maxima. Yeah. Now, if you don't understand now why the functional form looks like this for temperature less than Tc, please take it also as a homework. Just try to find out, if you take the functional form minus psi square plus psi to the power 4, what should be the value, where should the maxima and the minima lie, okay? For the time being, I'm just telling you that if you are at the temperature below the critical temperature, the functional form is given by the red curve line here. All right, now, you know that the equilibrium state of a system is dictated by the minimum of the free energy, right? So that's, I hope that you have already come across in the statistical mechanics course. So you already know the concept of free energy and the equilibrium configuration of the system, okay? So whenever I'm trying to find an equilibrium state of a system, it refers to the minimum of the free energy. So now let's start with the situation where I take the same binary liquid mixture. It's at a very high temperature, much higher than the critical temperature, okay? Which means that it's in the homogeneous phase, right? Like I told you before. Now, if you look at the functional form here, temperature higher than the critical temperature corresponds to the green curve here. And what is the minimum here? It's only one minimum where the value is 0, right? So this point here, this 0, 0 point here, which is marked by the green circle here, the filled circle, that corresponds to the equilibrium configuration of the system at the high temperature. And like you see, the order parameter is indeed 0 here, which means that it's in a disordered state or it's a completely homogeneously mixed state, okay? Whereas if I take the system, which is at a very low temperature, say it's at somewhere here, all right? The equilibrium configurations are given by the red circles here. And there are, of course, two possibilities. It might be the situation where you have the A domains are more prevailing or the B type of particles prevailing, right? So if you look at the phase diagram here and you just look at the temperature, you just draw a horizontal line here, any temperature which is below the critical temperature, you see there are 2 points, coexistence points. One will correspond to the majority of A particles and the other will correspond to the majority of B particles, right? And those 2 points are actually being corresponds to these 2 minimum of the free energy functional form here, okay? So now let's start with the system, which is initially at a very high temperature, T equal to Tc. And at this temperature, the system is homogeneously mixed and the system is sitting very happily here at this green circle here. It's in the equilibrium configuration. And then you suddenly change the temperature of the system below the critical temperature. So what happens now? This equilibrium state, which was being dictated by the green circle here, now it has become an unstable point, and the new stable points or the new equilibrium points should actually correspond to these red circles here, right? So the system should try to go from the green circle to one of these red circles. And as it goes from this green circle to the red circles, it actually undergoes a non-equilibrium phenomenon. And that phenomenon is known as the phase separation or spinodal decomposition or domain formation, the terminologies which you have come across in the talk today. Okay, so that's what is meant by the phase separation. So to come back to the questions which you have posed, why does the phase separation happen at all? Well, it happens because you change the temperature of the system very quickly. So the system moves out of equilibrium. It tries to go to the new equilibrium state, and the intermediate non-equilibrium process is the phase separation. Okay. So while this phase separation goes on, you actually have domains forming, like you see in this picture here. These domains, so initially the domains are very small. Then as time progresses, these domains get bigger and bigger, and until finally in the equilibrium state, you will have just, two the phases, the two domains which are just coexisting with each other. Now, what about the domain wall? So if you look at the two walls domains here, for example, in between two domains of different species, you basically have an interface, right? And that's what is known as the domain wall. All right. So, okay, so if you have any other questions, please keep posting the questions in the chat and I'll pick them up at the correct time, okay? So I hope I have convinced you that this spinodal decomposition, it basically is happening because the system is trying to go to the new equilibrium state. And this is the situation which I explained to you. It's mainly in the bulk, okay? Now, you, in addition to this kind of phenomena which is going on, if you have a surface or if you have a confining surface, then the effect due to that surface will also come into the picture. So the non-equilibrium process which will go on there will be then affected by the properties of the confining surface. And that is something which is known as the surface-directed spinodal decomposition, which I showed you before, okay? All right. So since I'm talking about I explained to you the spinodal decomposition already, let me just touch upon another example which I explained to you, which was the colloidal particle. Yeah. So if you remember, I showed you that this is a very interesting and very active topic of confined fluids at the moment in the scientific community. It's a very hot topic where you have laser activated Janus colloidal particles, which you put into solvents, binary solvents. And then when you turn on the laser illuminations, you see that the particles actually undergo active motion, all right? And the question is, of course, why? So to understand that, let's have a look at this picture here, okay? So this is the phase diagram, which I already explained to you. Now, this phase diagram is slightly different from the one that I showed you before, in the sense that if you remember the phase diagram that I showed you earlier, temperature higher than the critical temperature corresponds to the homogeneous phase. So this kind of phase diagram is known as an upside down coexistence curve, whereas in this type of system, it's the inverted one, yeah, which means that below the critical temperature, the system is in the homogeneous phase, and above the critical temperature, it's in the two-phase coexistence region. So what happens now is that you take this colloidal particle, okay, and you shine laser on it. So when you shine laser, this particle absorbs the light and it gets heated up, okay? So the part of the fluid which is close to the colloidal particle, that will also get heated up. Now, if it gets heated up, it means the chances are high that it will enter into this the binodal regime, and it will try to have phase separation happening at that temperature. Whereas if you look at the system which is far away from the Janus colloid, so there the temperature, the effect of this heating effect has not really propagated yet. So maybe there's a part of the fluid which is still at a temperature which is at the, it's still in the homogeneous phase. So in such situation, you actually have a part of the system where you have phase separation going on and a part where it tries to prefer to stay in the homogeneous mixed state. And in such situations, you can have the particle which is undergoing some kind of, active motion. Okay, so with that, then I will move on to the next topic, which will be mainly about the critical point, which I was talking about. Before that, there's a question, so I'll just try to pick it up. What happens to the entropy? Well, if you have a system which is at a very high temperature, if you have disorder which is very high in the system, the entropy is higher, right? But if you have a more ordered system, the entropy is lower, right? You know that. So the entropy is a measure of the disorder in the system, right? Okay, there is a question from Anubhav. I understand the process and the reason for domain formation, but what is the role of the surface here? Okay, so the surface, what it does is that typically the surfaces happen to have a preferential attraction to one of the two components of the fluids, okay? So I have, say, A and B type of particles, and the surface, it prefers A type of particles. What it means is that when you have this non-equilibrium process going on, more A type of particles will try to go to the surface. So you will have a layer of A type of particles forming on top of the surface, okay? Now, instead of A type of particles, say it prefers B type of particles, you will have the layer of the B type of particles forming. Or you might have a situation where the surface is neutral, which means that it doesn't have any affinity, preferential affinity to one of the two, attraction to any of the two species. So in such situations, it's a neutral system where the system itself basically determines how the structures are forming. Okay. There's a question that, let's say there was no surface. Even then, should there be any domain wall formation on lowering the temperature? Yes, of course. Irrespective of whether you have a surface or you don't have, if you don't have a surface, let's say it's like a bulk kind of situation, you will still have phase separation upon lowering the temperature. The only difference is that if you have a surface, the effect of the surface will come into the picture and it will change the properties of the non-equilibrium phenomena which are going on. But if you have a surface or you don't have a surface, you are going to have phase separation, you are going to observe domain wall formation. Okay? All right. Okay, so with that, let me move on to the other part, which is namely about, so let's now try to have a look at some of the properties of this critical point, okay? So you remember I was talking about the second order phase transition or the critical point. Let's have a look at the properties of a few systems. What happens when you have a fluid close to it? Okay, so this is a very involved topic, which is mainly known as critical phenomena. And critical phenomena is something where basically one looks at different static and dynamic properties of a fluid or a magnetic system close to this kind of second order phase transition or a critical point. Okay. So the first picture which you see here is the phase diagram, which I already explained to you. The concentration of the A particles, which is on the x-axis, is already it's defined here. It's the same definition which I showed you before. Now let's ask the question that if I look at different static properties of the system, okay, namely, for example, say if I look at the magnetization, if I look at susceptibility, correlation length, specific heat, etc., how do they behave? Okay. Now, the answer to that is that if you look at the properties of the systems, they actually exhibit some kind of singular behavior close to the critical point. And in order to quantify this singularity, typically one defines something called a reduced order parameter, epsilon, which is basically T minus Tc by Tc, okay? So it actually tells you how far you are from the critical point in terms of the reduced magnitude, okay? All right, so typically when you take a fluid and this fluid is very close to the critical temperature, you have certain correlated blobs which are forming in the system. So you have this A and B type of domains which are going on, and you have noise in the system, okay? And the question is, this the noise that you see there, so that actually gives you a measure of the correlation in the system. What do we mean by correlation is that if I take the system and I make a change at one point in the system, how much the effect of this change at one point going to affect the part of the other system. So that is something which is captured in terms of the quantity which is known as the correlation. Okay, so the more they are correlated, they will be affected more. And the correlation length is a length scale which actually determines the strength of this kind of correlation. Or in other words, it actually dictates the this kind of what is called the code. Yeah, so it reflects to the strength of the correlation. Now this correlation length, so if you look at it, it actually diverges as you go close to the critical temperature, and it diverges with an exponent nu. So if you look at these exponents here, so these exponents are actually going to be the ones which are dictating the singular behavior. Now, first of all, let's have a look at this M, which is basically the order parameter or the magnetization. So I told you that the order parameter is basically the difference in the concentrations of the A and B type of particles. So basically, if you look at the system, you start at a temperature which is lower than the critical temperature and you move towards the critical temperature. Okay, and you see that the difference in the concentrations of the A and B particles, that is basically reducing as you approach the critical point, right? Which means that if I look at the order parameter, it has a finite value below the critical temperature, and at the critical temperature, it basically there is a jump, right? And above it, it becomes 0. So that's what is being captured by this expression here. And the exponent beta actually captures the singularity of this quantity. Now, similar kind of singularity is captured by other quantities, namely susceptibility, specific heat, etc. And these quantities which I'm talking about today, so we will come back to these quantities in detail tomorrow, just to give you the brief flavor of the static critical phenomena. So if you look at the values of these exponents, so namely say this gamma, nu, beta, alpha, etc., they exhibit some kind of universality, okay? And what do we mean by universality is that you might have different kinds of systems. For example, you might have a magnetic system, you might have a simple liquid, or you have a binary liquid. As long as the range of interaction is belong to the similar type, no matter which specific material you take, the values of the exponents are going to be the same. For example, in case of Ising universality class, it's basically called short range interaction, okay? So as long as you have systems whose interactions belonging to the short range interaction, the values of these exponents will all be the same, namely they will have these particular values. So this is called universality in the literature. And the interesting point here is that all these exponents that you look at, they are not all independent of each other. Okay, so there are certain scaling relations, like one example that I show you here. Okay, so you have certain exponents, not all of them are independent. There are some scaling exponents which are basically relating each of them. So these are some of the properties if you look at the static quantities. Now the question is, what happens if you look at dynamic quantities? And by dynamic quantities, I mean the transport properties. Okay. For example, you know that if I look at a system and I look at different kinds of transport properties, right? For example, you know there is something called viscosity, diffusivity, etc. How do the behavior of those quantities look like close to the critical temperature? Well, first of all, if you have a fluid which is close to the critical temperature, its relaxation time becomes very large, okay? Which means that if I slightly perturb the system, it's going to take longer time for it to come back to the any kind of relaxed kind of situation, okay? So this is once again related to the correlation length, yeah? And the relaxation time becoming very large means that the dynamics of the system is getting very slow, okay? Which means that if I look at the diffusivity of the system, it's going to be very small close to the critical point, right? Because the transport through the system is going to get very slow, yeah? Similarly, if I look at the viscosity is going to be pretty high because it's a system where namely the relaxation time has become very large. So if I make any kind of change, it's actually going to take large amount of time for it to propagate. So this diffusivity and viscosity, etc., they once again exhibit certain kinds of singular behavior, which are captured by these expressions here. And these singularities are explained in terms of the correlation length, xi, okay? Like I showed you, there are some kind of universality in the static quantities. The dynamic quantities, namely these transport properties, they also exhibit certain kind of universality, okay? And for fluids, it's known as the liquid universality class, which means that when you talk about liquid universality class, it means that you have mass, momentum, and energy conservation in the system, okay? And for liquid universality class, the values of these exponents are given here. So there are certain techniques called mode coupling theory, renormalization, group calculation, dynamic RG, etc., from which people found the values of these exponents. So there are also computational works with which the values of these exponents were obtained accurately. Okay? So nevertheless, the flavor that I was trying to give you is that if you take a binary fluid or any kind of liquid, a fluid which is close to the critical temperature, and if you look at the properties, different static and dynamic properties, you do observe certain kind of singular behavior. And those singular behaviors make the properties or different kind of phenomena which are going on in the system extremely interesting. So in tomorrow's lecture, we will focus on some of those properties. We will pick up some static properties as well as some transport properties in some non-equilibrium situations. And like you will see that if you look at the dynamics in an equilibrium fluid, whereas if you look at the dynamics or in case of a non-equilibrium fluid, in non-equilibrium, the properties are going to be much more interesting, involved, and more difficult to solve as well. So with that, I would like to conclude today's lecture. And from tomorrow onwards, we're now going to get into the properties of different static and dynamic properties, which are going to be close to this kind of critical point.